All right, everybody, we are back to your favorite topic, which is stoichiometry. And today we're talking about stoichiometry and thermochemical equations, and in particular, your very favorite limiting reactant style problems. And so this is designed to help you guys get through 7.4, the practice sheet that is assigned to you for this week. Okay, so let's just remember kind of what this stuff means. The amount of energy transferred either out of an exothermic chemical reaction or required into an endothermic reaction is completely dependent on the amount of reactants and products in the equation. Okay, so let's just start by looking at a thermochemical equation. Okay, so here's a balanced thermochemical equation. This is a really interesting reaction. This is iron oxide reacting with aluminum to make aluminum oxide and iron. And this is what you call thermite, and it is highly exothermic. This negative 850 kilojoules. That's a lot of energy being released in this reaction. Okay, and so where we are now with looking at these thermochemical equations is knowing that the delta H represents the energy transfer. The negative sign just tells you that we are decreasing in energy from reactants to products, and that means it's exothermic. Do not make the mistake of thinking that this is somehow some negative amount of energy. That's not the case. It's just the sign means it's exothermic, okay? So in particular, when we talk about stoichiometry and thermochemistry, we have to understand, again, that the coefficients that are in place here, and especially here with the reactants, have everything to do with this amount of energy produced. Okay, and so this chemical reaction, the balanced equation, is telling us that 1 mole of iron oxide, when reacted with 2 moles of aluminum, should release 850 kilojoules of energy. That's this 1 is right here, and this 2 is right there, right? That's what this is telling us. Now, if we adjust the amounts of our reactants here, then we're gonna have to adjust the amount of energy that is being produced as well. And that goes back to what we did with limiting reactant and the production of product. You know, we know that if we have different amounts of reactant from the balanced equation, we're going to make a different amount of product, and it's the same with energy. Okay, so like for example, if we had just 0.1 mole of iron oxide and 2 moles of aluminum, we would only make 1/10 of the amount of energy as given as our delta H. And even though we have the full required amount of aluminum, we only have a little bit of iron oxide to work with, and it's going to get used up in a hurry, and we're going to have a whole bunch of aluminum left over, and we're certainly not going to make as much energy as we would have had we used an entire mole of iron oxide. Also, you know, like if you doubled the amount of iron oxide and doubled the amount of aluminum, you would get double the amount of energy. Okay, and that's kind of what we talked about with mole to mole thermochemistry and stoichiometry. But now we're going to work into grams of substances and reactants. So let's just work with this equation since it's a pretty cool one. So this is a pretty normal type of question that you'll see. If 300 grams of iron oxide react with 175 grams of aluminum, how much energy is released? This question would probably look more familiar to you if instead of asking how much energy was released, it said something like how much iron is produced or something like that. And then you would know, all right, I gotta go through the steps of determining what is the limiting reactant, using the limiting reactant to then determine how many grams of a product would be made. But instead of using the limiting reactant to determine how many grams of product get made, we're going to use it to determine how much energy is released in the reaction. Okay, so we got to ask ourselves this hypothetical question. If all of the iron oxide is consumed, if all 300 grams of the iron oxide gets consumed, how much aluminum would that take? And, you could ask it in the other way too. You could say, if all 175 grams of aluminum were going to react, how much iron oxide would be needed? But I always just kind of work from left to right across the equation. So I always just start with this one and go across. Anyway, so that should be kind of a review to you, hopefully. And then after determining how much aluminum is required to consume all of your iron oxide, you got to compare that amount of aluminum to the amount in the problem, okay? And then if less aluminum is required than is given to you in the problem, then the iron oxide is the limiting reactant. Or if you get results like this, if more aluminum is required than is given to you in the problem, then aluminum is the limiting reactant, okay? So again, the amount of energy that's going to be released here is completely determined on the limiting reactant. Just like the amount of product that would have gotten produced is completely determined, dependent on the limiting reactant. So let's go ahead and go through our steps here. And when we do our limiting reactant work, let's see, where's that stuff? Oh, I guess I don't need it. So here's the work that goes into determining the limiting reactant, okay? So remember, this is like grams of A, molar mass of A, coefficient of B, and then the molar mass of B. And I've made, I want to consume all of the iron oxide, and I want to determine how many grams of aluminum that this is gonna take. Okay, so let's go ahead and calculate this. Let's see. $159.7. Okay, this 101.4 grams of aluminum, right? Okay, so here, to consume all 300 grams of our iron oxide given to us in the problem, it's going to take just over 100 grams of aluminum. So now we have to go back to the problem and compare that amount to how much aluminum we've been given. So here's the problem again. 300 grams of iron oxide, 175 grams of aluminum. So we certainly have more than enough aluminum to react all 300 grams of iron oxide. Okay, so that means that our iron oxide is the limiting reactant. And so moving forward, we need to base the production of the energy on the amount of iron oxide that we have in the problem, which is 300 grams. Okay, so to do that, we need to basically equate the number of grams of our limiting reactant to the amount of energy that would be produced based on that amount of grams. And so to do that, we got to go through moles first and then to energy. And here's what the dimensional analysis looks like. You start with your grams of limiting reactant right here. This down here, molar mass of the limiting reactant. And then this portion right here, this is like the energy to mole kind of ratio, where we use the coefficient of the limiting reactant, which is going to be 1 in this example, but it doesn't have to be. You have to look back to the balanced equation to see if this is what number this is going to be. And then the delta H value goes up here. And don't make the mistake of using a negative number here. This is always a positive number, even though it may look like a negative in your thermochemical equation. Okay, so here's what the work looks like. We have our grams of iron oxide because we determined it was our limiting reactant. There's the molar mass, and this is the coefficient from iron oxide. It's a 1 because remember our balanced equation. looks like this. That one is that one right there, okay? So the coefficient from the balanced equation is what goes down here, okay? And that's the one. Okay, let's calculate this and see how much energy gets released. This is the fun part, right? It's like, I feel like I did something wrong. Hold on. Yeah, okay, good. So this is 1,597 kilojoules, okay, of energy. All right. And so, you know, that's the amount of energy that is going to come out of this reaction, given that we have 300 grams of iron oxide. And of course, you know, we're going to have a bunch of unreacted aluminum left over. Remember, it only was going to take about 100 grams of aluminum to react all of the iron oxide, which means we'll have a little pile of leftover aluminum that didn't get reacted, and no more iron oxide, and we'll have released 1,597 kilojoules of energy into the surroundings. Okay, so that's one example of a limiting reactant thermochemistry problem.